Welcome everyone, I'm Brian Walsh, and in today's lesson we're going over the ideal gas law.
When dealing with ideal gases, you're going to learn about Boyle's law, Charles's law, and Avogadro's law. And you can memorize these things if you want to, but you won't need them to do your calculations. To do our calculations, all we're really going to need is the ideal gas law, which is this right here. So it's PV equals nRT. The P stands for pressure, which is going to be in atmospheres. The V here is for volume, which is in liters. The N stands for moles of gas, and that's going to be in moles. R is the universal gas constant, which is 0.0821 liters times atmospheres over moles times Kelvin. And the T is for temperature, which is in Kelvin. So what you have is pressure times volume equals moles of gas times the universal gas constant times temperature in Kelvin. If you're having a hard time remembering what units each of these things should be in, just look at your universal gas constant. And this will tell you what the units need to be. So this tells us that our volume needs to be in liters, that our pressure needs to be in atmosphere, N is moles, and T is Kelvin. By rearranging our ideal gas law equation, we can learn about the relationship between pressure and volume. For example, if we solve this equation for P, we get this. And looking at this equation, we can see that if we increase the volume of the container, we decrease the pressure. Because volume is in the denominator, and as this number gets bigger, this number gets smaller. And the reverse is true as well. As volume gets smaller, pressure gets greater. And if we want to solve for volume, we see the same relationship. The key thing to take away from this, though, is that when volume increases, pressure decreases. And when volume decreases, pressure increases. Now, as you go through this chapter, there are going to be some terms that it's important to know. The first one is STP, and STP stands for Standard Temperature and Pressure. And what that means, if something is at STP, that means it's at 273 degrees Kelvin and 1 atmosphere. Another relationship that you need to be aware of is standard molar volume, and this is true for ideal gases only. And what this tells us is that 1 mole of gas occupies a volume of 22.4 liters. So this gives us a conversion factor for ideal gases. So let's go ahead and look at a sample problem for ideal gas law. So we're going to be using our PV equals nRT equation here. And this problem says a steel tank has a volume of 438 liters and is filled with 885 grams of O2. Calculate the pressure of O2 at 21 degrees Celsius. So the first thing we want to do is write down all the information that we've been given. So they've told us that the tank has a volume of 438 liters, so we put 438 for our volume. They've said that we have 885 grams of O2, and this is not in moles, so we're going to have to convert it to moles, but for now we can write N equals 885 grams of O2. Our R here is a constant, so our R is 0.0821. And finally, they told us that our temperature is 21 degrees Celsius. And the pressure of the tank is what we're trying to find. So in order to use our equation and calculate the pressure, we need to make sure that our units are all in the right units. Which means that we're going to need volume in liters. We're going to need pressure is what we're trying to find. That will be in atmospheres. We need N needs to be in moles, and T needs to be in Kelvin. So we're good here and here, but we need to convert 885 grams of O2 to moles of O2. We also need to convert 21 degrees Celsius to degrees Kelvin. Let's start by converting our 885 grams of O2 to moles of O2. So we start with our 885 grams of O2, and we want to convert this to moles of O2. And we're going to do that by using the molar mass. So if we use our periodic table, we calculate the molar mass of O2 to be 32.00 grams per mole. So we set this up so our grams of O2 are on bottom to cancel with our grams on top. So these grams cancel with these grams, and we're left with moles of O2. We multiply 885 times 1 and then divide by 32. And what we get is 27.7 moles of O2. So now we have our N in moles, we have our V in liters, and we have our R, which is a constant. So now all we have to do is convert our 21 degrees Celsius to Kelvin. And to convert from Celsius to Kelvin, we just add 273. So we add 21 plus 273, and what we get is 294 Kelvin. So now we have everything we need in the proper units, and we can go ahead and plug them into our equation. So we plug all of our values in here, and now we're going to solve for P. And remember that all we've done here is plug these numbers into this equation. And now we want to get P by itself, so we're going to divide both sides by 438 liters. And when we do this, we can see that now we have 438 liters on top and on bottom here, which means that these can cancel with these. And if we look at the other side of the equation, we see there's other places where we can cancel units. So we have moles on top here and moles on bottom here. So these cancel. We have Kelvin here on top and Kelvin on bottom here. So these Kelvin and these Kelvin cancel. And now we have liters on top here and liters on bottom here, which means that these liters and these liters cancel. And we see then that all we're left with is atmospheres. So now we can do this calculation. We multiply 27.7 times 0.0821 times 294 and then divide by 438. And what we find is that the pressure is equal to 1.53 atmosphere. It won't always be as simple as just using PV equals nRT. Sometimes you're going to have to use this equation. You'll use this equation in problems where they give you initial conditions for one gas, and then they change one of the variables and ask you to find the new conditions. For example, this problem says a sample of methane gas occupies a volume of 9.1 liters at 198 degrees Celsius. Assuming that the pressure remains constant, what temperature in Celsius is needed to reduce the volume to 2.50 liters? So they've given us an initial volume of gas, 9.10 liters, and they've given us an initial temperature of 198 Celsius. Then they've told us that the volume is going to be reduced to 2.50 liters. And they're asking us what the new temperature is going to be. Now you might be looking at our equation here and thinking that we weren't given enough information. But since we're setting these two things equal to each other, anything that stays the same from one side to the next can be canceled. In other words, anything that remains constant from one side to the next can be canceled. In this equation, R is always a constant, so R can always be canceled from one side to the next. So we cancel R. The problem talks about a sample of methane gas, but nowhere in here does it say anything about adding more gas or taking gas away, which means that N remains constant also. And since N remains constant, we can cancel it on both sides. And then the problem tells us that the pressure remains constant, which means that we can cancel pressure here and pressure here. And now that we've canceled everything that remains constant, we can rewrite our equation to look like this. We know our V1 is here, we know our T1, we know our V2, so we can plug these in and solve for T2 now. But before we do that, we have to make sure that we have the right units. So we have our temperature here in Celsius, so we need to convert this to Kelvin before we can plug it in here. So to convert from Celsius to Kelvin, we add 273. And what we get is T1 equals 471 Kelvin. Now we can plug these values into our equation and solve for T2. So we have our V1 is 9.1 liters, our T1 is 471 Kelvin, our V2 is 2.50 liters, and we can solve for our T2. Now there's a couple different ways we can solve this, but we're going to cross multiply, which means we're going to take T2 times 9.10 liters and we're going to multiply them. And then we take 471 Kelvin times 2.50 liters. And we get an equation that looks like this. And now since we want to get T2 by itself, we're going to divide both sides by 9.10 liters. And on the left side here we have 9.1 liters over 9.1 liters, which means that those can cancel. On the right hand side we can see we have liters on top and liters on bottom, so those units are going to cancel. So now we divide 1177.5 by 9.10, and what we get is 129 Kelvin. But we're not quite done yet because the question asked us to solve for temperature in Celsius, which means that we need to convert 129 Kelvin to Celsius. And to convert from Kelvin to Celsius, we subtract 273. And when we do that, what we get is negative 144 degrees Celsius, which means that our T2 is negative 144.
If you have any questions about anything, or if you have any feedback that you'd like to give me, please leave me a message. You can leave a comment, or you can email me at chemistrymadeeasy118@gmail.com. Thanks for watching.